Thanks for the introduction. So first of all the credit go to the co-authors, especially the first author who did most of the work, including this slide. But unfortunately, they couldn't make it due to visa issues, so I have to present for them. But let's dive in. Cool. So the work is about local differential privacy, and in local differential privacy, we have two parts. The left-hand side is perturbation function. It's not magic, but just some probabilities, and that can transform your raw sensitive data into perturbed data. Okay, and in a way that satisfies local differential privacy definition. And on the right-hand side, we have the aggregation function that takes all the perturbed raw perturbed data Y, and try to get some usefulness from the aggregation, right? And there are some cool. And there are some fundamental tasks depending on whether your data is like categorical data, right? So you want to estimate like a gender distribution or education level distribution, or if your data is numerical, you want to estimate like age distribution or income distribution, right? And local differential privacy has been deployed in some real world cases. Again. Cool. Sorry, the TV is not synchronizing, but cool. Yeah, so for aggregation methods, we first have this very easy derivation of like a one-line calculation that can independently estimate the frequency for each category. Okay, but due to the noise added due to local differential privacy, there could be some negative estimation, or the frequency does not add up to 1, so it doesn't make sense, right? So there are therefore people have derived the methodology to ensure the consistency of the estimation, right? So basically just to make sure there's no negative estimation, there's the frequency add up to 1. And people also derive methods that can leverage prior knowledge, right? So for example, in many cases, the distribution follow roughly a zip distribution. Okay. A zip distribution, which makes sense, but if it does not follow zip distribution, you won't get good results. Another line of work uses expectation maximization method, shortly for EM method. The goal is to achieve a max likelihood estimation. So it's more like optimization, right? So you start from a uniform distribution and notch every estimation a little bit and iteratively, and hopefully you can get a pretty accurate estimation, right? By accurate, I mean your solution, EM solution, is close to the real distribution. And people have derived methodology for that as well. And I should know that this method is especially useful if you do not have this closed form explicit function to have independent estimation. So this work targets and focuses on local the EM-based method. Okay, through our experience, several years experience working with the EM, we made two observations. So basically, it has two shortcomings. The first one is, so how many of you are familiar with this figure, right? So in figure 1, it's basically look like a training loss, right? If you train a machine learning model. So basically, EM is also used in training machine learning models. It's like an optimization method, right? So you can expect after you train more and more iterations, there will be overfitting issues, and overfitting is bad. We all know that. The other shortcoming of EM, as shown in the figure 2, is the error for each individual category is roughly the same. But if we want to estimation for many categories, the error will accumulate. So we don't want that. So we want to, in this paper, improve EM on these two aspects. So the first one, first I want to dive a little bit more deeper into LDP, right? So people have shown that LDP noise roughly follows Gaussian noise. So if a true frequency is low, it's likely to be overwhelmed by Gaussian noise, and we know that. And the second thought is in machine learning, we typically use regularization as a popular method to overcome overfitting. So in this paper, we want to introduce this regularization into EM-based LDP estimation. Okay, so this is a high-level idea of our approach. So from the observed LDP data, we first run the EM method, and then the high-level idea of our key contribution is merging the less frequent items together. And we iteratively run EM and then merge, run EM and merge. Okay, so that's a high-level idea. And I won't go into the detail of the EM method, but basically we have to somehow write down the closed form explicitly the likelihood function for your estimation, okay? And then you have to derive the E step, which calculates the likelihood, and the M step, which maximizes the likelihood. And we can apply this generic recipe into LDP aggregation. And I also won't go into the detail of it, but if you are very familiar with EM, you should maybe you will find those very natural to derive. But here's what we introduce. Okay, so basically step 3 and 4 are what we introduce. Okay, so but let me start from step 1. Okay, so we start with the noisy data, and we have some initial mixture model, which is basically a uniform estimation. Or if you have some prior, you can use a non-uniform prior. And the R1 up to Rn are basically perturbation functions. So those, remember, the perturbation functions are those that satisfy local domain privacy definition. So we introduced that mainly because we want to incorporate many LDP protocols. Some are just a one step. In that case, the perturbation function is uniform across the population, but some are like a multi-stage. So we want to incorporate that as well, and our framework can incorporate that. Okay, and after that, you just run the normal EM. And then the reduction is shown in step 3, which is given, the example is given there. There's some mathematical formulation going on, but the high-level idea is just that you take the estimations that are below the threshold and merge them, and there's no, very simple and naive approach. And then step 4 is a criteria where you determine whether you want to proceed or you want to stop. Okay? We borrow the idea from statistics. There is this BIC criteria, basically trading off the benefit of doing more merging versus the loss, right? So it's a loss of log of the likelihood that the loss over there versus K prime is the more you merge, the smaller the K. Okay? Yeah, so we also introduce our approach to other LDP protocols. So there's more details in the paper, but we just list them. There are, I believe, the last one is a 2-stage LDP protocol, and there are also other details. And we also did a very a high-level accuracy analysis. Basically, we want to show that by using our merging strategy compared to the traditional EM, right? So we have a key prime over key improvement. Basically, the more we merge, the better the accuracy could be, but that's a really very high-level theoretical guarantee. Okay, I also want to show some interesting evaluation results. We did the evaluation on 3, 1 synthetic and 2 benchmark public benchmark datasets, and on 3 tasks and appropriate matrix. So first, on the three tasks, we can observe that our approach, the -MR method over there, shorted for mixture reduction. So because our method is applied after EM, right? So it has to be attached to an existing aggregation function. So we can observe some improvement, at most almost by half. And unfortunately, when epsilon is small or n is the size of the data set increase, basically these two, when n, epsilon or n increases, basically the relative amount of noise will decrease, and therefore, in those cases, our approach does not benefit. So that's also reasonable, right? So because in the extreme case, you have zero you have zero noise. Of course, you don't expect any improvement in any method. So this figure shows after we run a method for 100 times, we don't observe a clear systematic bias among all of them, but the other method will incur some systematic bias, and our variance is also smaller. And this also shows an interesting result on efficiency. So by merging, right, basically EM, the overhead is much slower. So we can achieve a much faster convergence rate, maybe like 3 to 5 times faster than previous method, basically traditional EM. So I want to conclude by a guidance of when to use our method, right? So basically, it's a merging method on top of EM, and it can be used in any. So it can be replacing, or you can understand it as an add-on on existing EM method. And when there are many categories you want to estimate, or when there is more noise compared to your ground truth data, you want to use that, but otherwise the benefit would be smaller. But that's all for the talk. I'd like to take questions.
Thank you. Thanks for the awesome talk. Anybody would like to ask questions? Okay, I have a question. Yeah, really awesome work. For the slide of intuition of solving the overfitting issues, can I adapt this kind of intuition into other fancy models like transformer or others? Yeah. Would you like to share your insights about this?
Or
maybe future.
Yeah, maybe. Yeah, but because it's far from LDP, right? So it's a transformer. It's in the machine learning. Yeah, I hope it can be applied, but I don't really know.
Oh, thank you. Yeah, that's really future work. Okay. Yeah. Any other questions? Thank you.